Okay, welcome everybody. So today is going to be our first seminar of the year, and I'm very happy to introduce Professor Joaquim Gomis from the University of Barcelona, who is going to talk about like worldline actions for fractons. Please, Joaquim, go on.
Okay, thank you for the invitation, and let me say that the title is this worldline approach to some scalar fracton theories, and that is based on this paper done more or less recently, and the plan of the talk will be the following. Since I assume that maybe some of you don't know about what is the worldline approach to quantum field theory, I am going to discuss a moment that sort of thing. After will be some general properties of fractons that probably most of you know more than me. And after I will connect how some of these properties of the factors can be seen at the level of the worldline, at the level of the particle models. And I would like to conclude and give possible outlooks so that one could follow, at least from my perspective. I'm sure should be others. Okay, the first thing is, for those of you that you don't know the worldline approach to quantum field theory, is something that has had a long history, because essentially was invented by Feynman in some of in the appendices of his works of 1950, and later has been developed for many people, and nowadays it is used as a tool to understand quantum field theory at tree level and loops, and there are a lot of applications. What I will do is easier for me to explain my own work on that it goes back to 1974. And as in a sense, this is a first step in this direction of making the connection of the worldline approach and the quantum field theory. And you will see in which sense I'm saying this a first step.
Can I interrupt you 1 second?
Yes, please.
Maybe it's convenient if you go like full screen on your slides, like pressing the green button. Because we cannot see the full slide.
Well, how I do
the green circle.
The green circle.
Yes. Click on it.
Like that.
If you do that, well, we can see the full thing, but
okay, perfect. No, it's much better for me.
I don't know if it's better.
Perfect. Therefore, I was saying, sorry?
I think it's better as it was before, because now it's too small. What we see is like too small. Sorry, wait a second. People is saying in the chat that it's better. So, okay, just keep it like this.
I keep it like that?
Yes, the audience is saying that it's better.
Okay. Therefore, the key point of the worldline approach is change what are the fundamental variables. And the point is that you change your fields by the coordinates of the particle. That, for us at least, was inspired by string theory. In string theory, the fundamental object is the string worksheet, and the field theory string was done later, but initially was done in the first quantized approach that was called. And in here, it's an imitation of that. Therefore, instead of having a string worksheet, we have a string Worldline. Can you see my cursor here?
Yes.
Okay.
Yes, we can.
Therefore, this is the Worldline that is parameterized with some parameter tau. Therefore, the point is that we are going to substitute the field x mu by the coordinate of the Worldline that is parameterized by tau. The free action is given by the length of the particle, as you know very well, and the momenta is proportional to the some unit vector, and therefore the square of it gives a primary constraint in the direct sense. And here are the Poisson brackets, and here is the metric that we were using in that time. And this action is diffeomorphic invariant because it's homogeneous with the first degree velocities, and also is Poincare invariant. Now, according to the Dirac, we should add to the canonical Hamiltonian the primary first-class constraint, or the primary constraint, and the result being homogeneous with the first degree in the velocities, the canonical Hamiltonian is 0, and there is only the remaining primary constraint with an arbitrary function of tau. The point is that this is, since invariant diffeomorphism, we could choose the proper time gauge that is essentially choosing lambda equal to -1/2n. And the Lagrangian becomes this thing here. If we want to quantize the model, what we should do is to apply the constraint on the states, and that represents precisely the Klein-Gordon equation. Okay, now, but we will be we will be interested in computing the propagator of the in a path integral form. Therefore, what one is doing is computing the transition amplitude as a functional integration on the coordinates of the particle by the corresponding Lagrangian, and C is something that should be determined by this normalization condition. The Rodinger equation now, it is not respect to T, but respect to this parameter of the Worldline, and the wave function is simply this scalar product. And the constraint, we will be considering physical objects as physical wave functions, the ones that are annihilated by the Klein-Gordon equation. And how do we obtain this physical field? And that we do by an integration of epsilon x tau with exponential e to the 0 tau, that is the projection on the 0 eigenvalue that corresponds to taking 0 this, because there is the constraint. Therefore, that's our definition of doing the physical, or was our definition of doing, of computing the physical amplitude. Nowadays, and later, our work has been much more refined things because, for example, since it's invariant under diffeomorphism, should be the volume group, should be, if you wish, the Faddeev-Popov procedure, introducing Gauss, BRST formulas, and so on. But I explained what we have done in '74. I assume that that some of you were not around at that time. Okay, that if we compute this transition amplitude, we got some expression that one could do because it's quadratic. And when this is written in terms of this in momentum space and Fourier transform, this is given by this action here. And the important point is that this depends only on T minus F. Therefore, in order to preserve that TF is greater than TY, we integrate in order to get the physical propagation. Oh, sorry, I am making a little bit of a mess. we should integrate in order to get the physical propagator among 0 and infinity, and this it gives this ordinary propagator that corresponds to the Fourier transform of the Fourier two-point function of this free scalar field. At the moment, we are considering free fields. What about global symmetries? We have the symmetries of the particle are essentially Poincaré and given by this expression here, and the corresponding transformation and disclosed under the Poincaré group, and the transformations on the field are given by those expressions here. Therefore, we can go from one to the other in principle. Now, the point is, this is a free theory, but we want to do an interacting theory. We want to, in a sense, our goal in that time, we're recovering the vectors of the phi cube theory. And our inspiration was a paper by Maldestam that was called Joining and Splitting Strings. That in that time that was done in LightCon, but more recently is one who could do better. And here you see we have essentially the only vertex that we can do with the strings is this one. We have two strings that join in one. At the level of the particle, the thing is much more complicated. The particles are much more complicated in the sense that the strings, because we could have or something like 3 lines that join, or 4 lines, or okay, we have infinite number of possibilities of diagrams with particles associated to those one here. By the way, it was known in that time already that if you do the field theory limit of the scattering amplitude, the Veneziano amplitude, you recover the tension infinite limit, or the alpha prime going to 0 limit, you get the phi cube theory. Therefore, we were mostly concerned on this phi cube. Therefore, the point is, now, these are our fundamental variables, and we want to do, this is a geometrical interaction in the same way that this is a geometrical interaction for the strings. Therefore, this means that we integrate functionally over this point all the free action, but on the path that are given by this vectors here. This is the basis of introducing interaction. At least that was our initial point of view, of introducing interaction for the particles. Nowadays, maybe it's done better, but okay. For me, it's enough to that. But in a sense, let me already say why I'm doing that. Because fracton, at least certain class of theory of fractons are scalar theories. Therefore, the point was, can we describe these scalar theories changing the variable, or the role of the variable filled by the role of the variable, the coordinate of the particle, and can we do as we did in this phi cube theory of calculating the propagator and studying the interactions, that these will be interactions among fractons. And essentially that was the motivation by our recent work. Okay, the point therefore, how we do integrate on this type of lines. Okay, we integrate simply from the particle 2 going to particle point 0, and from the point, sorry, no, it's in the opposite way, from the point x2 going to 0 and the from 1 going to 0, we have that sort of thing. And finally, this is the one is this vertex and the other are these lines. And if you do the calculation and you do in momentum space, you find this sort of thing, the delta function and the product of the external propagators. And that is precisely the vertex, the Feynman rule of the vectors of phi cube theory. And we have not done more in that time. We were not in that time was not fashionable. I think was becoming fashionable, this field theory by strings by Polyakov and later by Strassler, Schubert. Okay, there is a lot of literature that I didn't care, excuse me, so much in giving you, but there is a lot of things that you could do with this Worldline approach of field theory. Now, let me say some general properties of the fractons. As I'm telling you, since I am not a condensed matter physics, my knowledge on that is very tangential or very in only particular direction. But from what I understand, the K points are the infinite degeneracy, the infrared ultraviolet mixing, they are non-Lorentzian symmetry, they contain not ordinary rotation, but discrete rotations, and there is this new phenomena of subsystem strings. Okay, let me go now to consider the subsystem strings. I am using to write in this iPad, sorry by my bad writing. Hopefully you can see what I'm trying to say. I wanted to copy a PDF inside this notability that I'm using, and I have been unable. But the essential point is the following. Let's consider the XQ model, and we have ordinary spins, and we have a global symmetry when we change all the spins up and down. But if we have layer, by the way, here is a 2 + 1 dimensional theory, I think. This layer I can do in this plane, and here we have direction X and direction Y, and there I can have independently flipping the spin in the directions X and the direction Y. And that is what is called the subsistency. Okay, now here I am writing this. In every plane, we have two zeta2 symmetries. These symmetries take ground states to ground states. Now, going to field theory. I am not going to say anything more about lattice model, and I'm considering this 2 + 1 dimensional field theory based on compact scalar that is obeys this periodic Binder condition. It seems that this was introduced by these guys, but I learned this from Seibert and Shao, and that's the action that we have in here. Okay, it's a free action that it contains derivative respect to time square. Instead, there are 4 special derivatives in the special coordinates. If you compute the equation of motion, that's given by this expression here. Sorry. And if I introduce this sort of currents, mu0 derivative respect to tau and jxy as mu tilde derivative j derivatives y, the equation of motion that you see here can be written as this sort of, let me call generalized conservation. Okay, if we have that, immediately we can see that there is this subsystem symmetries, and we can do in the following way. We take some particular value of x, and we consider the integral of jt integral in dy of jt. And the point, if it's a symmetry, the Noether theorem says that the derivative, the time derivative should be 0. And in fact, it is, because the derivative of this one is the derivative of time respect to jt, and this, using the equation of motion, is essentially equal to 0. Therefore, for every x, we have a symmetry. Therefore, clearly we have an infinite number of symmetries because X could take any value. And we could do analogous thing for the Y direction. We can consider Qy as the integral of dx of djt, and again, doing the same sort of calculation, you arrive to the conclusion that this is a conserved quantity, and that are called subsistent symmetries. I don't know who was the first to introduce that. If I recall properly, the first person, I think, was fracton, but I have not read the paper. And now, following a terminology, okay, first of all, one can compute what is the dispersion relation of this free theory, and essentially is given by E squared equal to some dimensional full constant P x squared Py squared. And this is called by these guys, Katz and Ras, the papers in 2021, the 2-4 model. 2 states for the number of the power of the energy, and 4 states for the total number of special derivatives. Now, the point it is, if we are with t equal to 0, we have e equal to 0. This will be the fracton, but the point is that for any value of pi, therefore, in that sense, it's clear that here there is this infinite degeneracy. That's the first thing. And the other is that there is this other phenomena that is the ultraviolet infrared mixing, because we are in the infrared taking equal to 0, but pi could be or in the could be as large as we want. Therefore, it's a theory that mixes things. But this, maybe for those of you that are not practitioners of field theory in or strings or something like that, this, if you consider non-commutative quantum field theory, this phenomenon occurs, and that was first discovered by Mingwala. I can pronounce this name, Van something, and Cyber. And essentially, the non-commutativity was saying that the coordinates do not commute. X with X does not commute, but the xi commutator j is theta j, and theta is theta j is different from 0 in the present non-commutativity. When you do the quantum field theory, you observe this phenomenon. Now, let's go to what we have done in our paper with Diego and Roberto. I mean, Roberto Casalbuoni and Diego Hidalgo. Okay, we do the following. Okay, if we know that we should consider as a fundamental value of the coordinate, let's try to do that. But instead of using the ordinary Marshall constraint p squared minus m squared that was the natural one for the relativistic particle, we consider another one. Really, if we consider a massless particle that I did not consider, didn't consider in our case many years ago, the constraint will be p squared equal to 0. Therefore, in a sense, the Marshall condition of this fracton is like is a sort of p squared equal to 0, but when I have introduced, I have modified the part associated to the spatial part. And that's the modification, is nothing more than the previous model. That is the dispersion relation of the Marshall condition. And therefore, what we do is, okay, let's consider the canonical Hamiltonian associated to a particle that has this Michel condition. Therefore, in order to do that, we should say what are the Poisson brackets. And giving the Poisson bracket is essentially giving this sort of thing here that I call, this is E with T, the Poisson bracket of E of T with E is -1. Instead, the Poisson bracket of X with P is flat. Therefore, and here I introduce a Lagrangian multiplier lambda, as was in the case of the master relativistic particle. Here's the Michel condition, and here this is imposing the primary constraint. The momenta of the lambda is a primary constraint and is multiplied by an arbitrary function, and that's essentially the Dirac Hamilton. Okay. Which are the configuration space coordinates that we have are T, X, Y, Z, and lambda. And the derivatives that appear in here are the derivatives of the Worldline parameter. Okay. And easily we can compute the corresponding equation of motion, essentially Hamilton equation of motion. And let me notice that the primary constraint, that the lambda is constrained to pi lambda equal to 0, that is the primary constraint. But if you remember the Dirac analysis of singular Lagrangians, if you have a constraint, you should ask what is the stability, because this defines a surface, you want that your trajectories are tangent to the surface. And if you do that, it results that there is a secondary constraint that is precisely the Michel constraint of the dispersion relation. But if you are interested in having a configuration space, what you should do, I mean, in the previous Lagrangian, P is non-dynamical, and you could eliminate through their own equation of motion, and you can substitute back. And here it is this question that this Lagrangian, this will be, if you wish, the analogous of the Polyakov action that he wrote as x squared divided by E, x squared meaning the fourth vector. Okay, but we can do also more. Lambda is a non-dynamical variable. We can use the equation of motion, and we can find that lambda is equal to that, and we have this expression completely in configuration space. And here we can have this, or consider, if we consider these absolute values, we have this alternative expression, that is the same thing. And what are the discrete, you see immediately here, there are discrete global symmetries, are special rotation of 90 degrees, x going to y, and y going to -x. And we have special inversions and t-inversion. Very good, those are discrete symmetries, but the question is, what about the continuous symmetries? And the point that we were following is the following. You consider the most general canonical point transformation. And what it means point, it means that it's linear on the, most linear on the momenta, here energy, here px, here py, and there is all here p lambda, and there is also a possibility to have a term independent of the momenta. And obviously, doing the Poisson brackets of that, we know that the transformation of t and xi, where is I and j will be 1 and 2, x and y, will be given by these Poisson brackets. Therefore, at this point, these are arbitrary functions, but we want this to be a symmetry. Therefore, we should impose that this is equal to 0. Here I make and this is a calculation that one does easily, but the essential point is that when we are taking here this part here, the time derivative will be the time derivative of pi lambda dot that was given by the equation of motion, and the other will be gamma dot multiplied by p lambda. But this time we do not consider, because the primary constraints at the level of the Lagrangian constraint are identities. Therefore, when you do the calculation, that's the only thing that you are allowed to do, use the primary constraints. If you do that, we arrive to some sort of generalized or killing equations associated to that, a differential equation, partial differential equation by these unknown functions. And let me jump. This is written explicitly in our paper. Some of the integrations are trivial, and the solutions are given by these ones, and these are finite dimensional. And you see this thing here, it is precisely the transformation of delta t. This is the transformation of delta x, and this is the transformation of delta y, and the transformation of lambda is given by this expression here. The generators that we have, for how many parameters we have here, we have parameter chi0, eta0, and a1. We have essentially 5. Okay, let me count. 1, 2, 3, 4, and eta 5. Okay, and the corresponding generators are given by those ones, and this close under a finite dimensional algebra. Let me note that there is not a special conformal transformation. And a fracton configuration with E equal to 0, px equal to 0 has a restricted mobility, since it only can move in the y direction. Okay, therefore fractons, I didn't maybe said before, are such that are immobile or this restricted mobility. Now, what about the subsystem symmetries? How can we get that? And we came across with the following idea that's is given by the root function. That is essentially doing the Legendre transform, but not in the all variables, but doing a partial Legendre transform. And if we do that, and we want to do a partial, we want to do the Routhian of this one, and this time we do not consider the x or px really as a dynamical variable, and that's the Routhian. Okay, that's the expression of the Routhian. And one compute the equation of motion, and the equation of motion are given by those ones. Px is like a parameter, like the mass, and therefore if we pass from that action that is in canonical form to the configuration space form, we arrive to this expression here, and you will recognize that this is nothing more, this thing here is nothing more than the motion of a massless relativistic particle in 1+1 dimension. And we know that which are the symmetries of a conformal particle in 1+1 dimension is infinite dimensional, is the conformal group. Therefore, this conformal group is a part of the subsistence symmetry. But clearly, you could do also in taking the partial Legendre transform, where now this time you take as parameter, if you wish, pi I, and the corresponding action results to be this one also of a massless relativistic particle in 1+1, but this time instead of x, instead of y, we have x. Therefore, also here we have an infinite dimensional symmetry. Now, I don't know how I am going rather quick, but please, if you need to interrupt me, don't do it. Now, in our paper, we do a collection of other models, other fracton models, following the terminology of Karsh and Ras, given by this pair ME and NP, and these are essentially ME. It says the number of the the power of the energy, and MP the power of the momentum. In that sense, that is this twofold, okay? And inside here, we have two classes of models that we can consider. The ones that are invariant under 90 degrees and are quartically on the momenta, or there is a second class where they are invariant under rotations of 180 degrees, and they depend on the spatial quadratic and the spatial momenta. And one can pass from one to the other simply by thinking that this pi squared goes in pi. Okay, that's I am referring to this work of Kars and Ras that we did in our paper. For example, let me give two types of examples. This is in 2+1 dimension. Obviously, this can be done in more dimensions, but we have some notes on that, but we didn't put in the paper. Okay, the point is, what will be the one-form model? The one-form model will be such that we have 1 power of the energy and 4 of the momenta, and that's essentially the Marshall condition. And if you construct the canonical Hamiltonian, you eliminate the momenta, and you eliminate the Lagrange multiplier, you arrive to this equation of motion, to this Lagrangian. And here you can observe the following thing, that still here it is invariant under 90 degrees, and there are special inversions. A curious thing that, honestly, at least I should say myself, maybe my collaborators understand this better than me. If you go for the continuous symmetries, the Lagrangian, the continuous symmetry of this Lagrangian coincides with the one of the two-form model. I mean, I don't have really a deep understanding of that. It's really a matter of the calculation, but hopefully there is some physical reason for that. If we go on to the Routhians, in a sense, I go to look for the subsystem symmetries. What are we going to get? In this case, is the Rodinger algebra. I didn't write to you. The Rodinger algebra, for those of you that you don't know, that probably you know, but okay, let me say again, it is the Galilei algebra that is 10-dimensional, plus the central extension that it makes the Barman, plus the dilatation and the special conformal transformation that sometimes are called expansions. That is the most general symmetry algebra of the Rodinger equation. Okay, I didn't write explicitly. Now, an example that also I want to discuss is the this 2,2 prime model, and you will see why in a moment. You see, the difference with I am using essentially this fact here, okay? The p squared going py in the 2,2 model was p dot square x p dot px squared py squared. Doing that, this go in the linear, and we have this sort of thing. If I compute, again, I can go to the canonical action, and from that, eliminating momenta, go to the configuration Lagrange. If instead of using coordinates x and y, I use these coordinates y1 and y2, the action, it becomes this one that you could recognize as a massless particle, but this time in a space that has 2 times. You see, there are 2 minus signs. That's a characteristic of that. In that case, it results that the symmetry algebra, it is a conformal group, but since we are in 2+1 dimension in this case, it results that it's finite dimensional, and it is O3,2. And here it starts maybe some thing that I would like to discuss. Oh my God, maybe I did too quick. Okay. let me say the following thing. Let me take to see what are the subsistent symmetries, and therefore I do the Routhian, and doing the Routhian, we find this expression here, where Tx here is a parameter, like a mass, for example. For those of you that have in mind what is a non-relativistic particle in a diffeomorphism invariant way, in 1 + 1 dimension will be essentially x dot square or y dot square divided by t dot. Therefore, here has been the change of t by y. And that the change of t by y, it is the one that passes from the Galilei, Barman, or Rodinger to Carroll. Therefore, the Routhian for this case is given by this Carroll-Rodinger algebra. By the way, let me say one thing about that algebra. Let's forget a moment about dilatations and these special conformal transformations or expansions. This, in 1 + 1 dimension, that will be, if we imagine, no, without imagine, we have gt equal to h and j with h equal to m. That is the Carroll algebra, and one can check, and that's important, that in the Carroll algebra, the particles do not move, and essentially the idea will be the following. The Carroll group was invented by Lévy-Leblond, I think in, I don't know, maybe in 63 or 66, really a long time ago, even before I was doing physics, in the following way. I mean, if imagine, I don't know, you cannot see me, okay. Imagine you have a cone. I mean, in the relativistic case, we have the light cone, we have the cone. Now, and imagine we do the non-relativistic limit, but really making the cone becoming flat. That is the C going to infinity limit. But Lévy-Leblond invented a new limit that was the C going to 0 limit. Therefore, the light cone this time collapses in the vertical axis. Therefore, if you consider a time-like particle that should be inside the light cone, or this particle could not move. Therefore, Carroll particles do not move. Therefore, it's not so strange that there is a relation among fractons and Carroll symmetry. Here we have seen this at the level of the subsystem symmetry. And why is so? This is because in 1 + 1 dimension, we have there is an isomorphism among the Carroll algebra and the Barman algebra. And the isomorphism comes from changing P into H. And that, for example, we were using this fact in a more general case of for Newton-Hooke algebras that are associated to the harmonic oscillator in this paper with Diego and Patricio. But that was a particular case of a more general thing that we have found with Andrea Barluccio, Roberto Casalbuoni, and myself in 2018, where this time we don't have an isomorphism, but the idea is that if you change h by t by x vector, you pass what the level of the generators by h going to the translation, you pass from Carroll to Galilei. Now, let me conclude, and I will maybe, since I see that I have going very fast, you didn't ask me anything, and I conclude with the following thing. Okay, we started to construct the Worldline approach to scalar fracton field theories. The subsymmetries appear by considering the Routhians of the particle Lagrangians. we have in our paper extensions of the to pseudoclassical Worldline fractons. Let me explain a little bit of that, and that is related to work by Andrea, Roberto, and Luca Luzana, and some other guys, but I learned these things from them in the following sense. Okay, we have the free relativistic particle, and we have constructed. And this, when we quantize, we have the Klein-Gordon equation. But we know that there is also the Dirac equation. Therefore, the question will be, can one construct a particle model that has as constraints one that is giving the Dirac equation? The Dirac equation, if you wish, being a fermion, the natural way will be described by Grassmann. And in these papers, they were constructing a particle, I call here pseudoclassical in the sense that it still is a particle model, but not only depends on the coordinates x, but depends also on the coordinates on the variable Grassmann variable coordinates. But the model is constructed in such a way that has two first-class constraints. One, that it gives us the case of the bosonic particle, the Klein-Gordon equation, and the other, it is the one that gives the Dirac equation. Therefore, in our paper, if you wish, since I have time, later I can share the our paper and can explain that there we constructed in a way the square root of the Marshall constraint E squared minus the model 2,2. But for us, and maybe this I pass the question to you guys, is there any fracton field theory such that contains the a sort of Dirac equation? Can somebody answer to that?
So is that a question for us?
Yes, yeah, no, I want to learn. I mean, I'm giving this seminar, but also I want to have the advantage that if I understand correctly, I'm talking to an audience that are mainly condensed matter physicists. Therefore, they should know. Okay, I'm sure you guys know much more than me on the condensed matter aspects. Therefore, what I am asking is in the same way that was this scalar field theory, or this, okay, didn't talk about that, this U1 electromagnetism by Precco. My question is a sort of Dirac fracton theories?
Okay, so yes, I mean, certainly we can have like some discussion about that, but then I would like first to ask the audience if they have any questions, and then we can move to some discussions.
Okay, good. Therefore, here we constructed these pseudoclassical models. We constructed also in our paper. I can share later if you wish. Our paper, we construct some fractronic strings. I mean, the number-Goto string has two constraints that are essentially ps squared plus x prime squared plus, and there is another constraint that is the scalar product of px prime equal to 0. And we generalize this in the fractonic sense, in the sense of not having something like that is quadratic, and I can tell about this if you wish. Sorry. Sorry. No. Okay. Now, things that, from my perspective, without, again, saying that I don't know how useful this could be for quantum matter physics. I hope that the answer will be yes, in the sense that there is a natural way that you can do this geometrical approach, this Worldline approach, where you want to construct geometrically your interactions. Therefore, a question that comes to my mind is that can we construct a sort of phi-cube theory for fractons? Is this making some sense? But in order to do that, one first step is that one should compute the propagator of the particle, and this we have not done yet. Therefore, these two things will be probably in direct application to what already maybe is known in the ordinary approach. And next thing that came to my mind was the following. With Roberto Casalboni, we constructed a model of two particles that have conformal invariance. And since conformal invariance, and let me say that this particle model is given by this expression here. We have px1, here, I didn't put the indices mu, particle 1, particle 2, one in bind, one other in bind for the particle 2, and here the interaction. It results that this model is conformal invariant. But the fractons essentially are a modification of these Marshall constraints. Therefore, another way, I don't know if this has been done in the literature, constructing the interaction among two fractons of different type. Okay, by the way, the analogous of the here is missing equal to 0. The analogous of the Klein-Gordon equation is given by this expression here. And that is what I was thinking, another way of introducing interaction among fractals. And another one that I have really no idea, I didn't try at all, but I think that maybe it's possible, will be to do the Worldline formulation of U1 fractals. Because I know from a paper of Paul Townsend, of Bernici, others, I don't remember now all the names, where they construct a pseudoclassical model, again, doing a generalization of these models done by other people, but for instead of n equal 1, putting one class of Grassmann variables, putting two classes of Grassmann variables, and they were obtaining the pseudoclassical description of a tensor, an antisymmetric tensor. Therefore, since in the Worldline formulation that I'm not familiar, I should say, I know that some of you have been working on that, it is symmetric. Therefore, the idea is, can one make a formulation of particles such that one can have, given the a formulation of the symmetric tensor theory? If the answer is yes, one can do a lot of things here. And maybe it's good that I stopped here, and if you have questions, we can discuss some more.
Okay, thank you for the nice talk. I think it's time for questions. Yes, we have time for some questions. So if anybody in the audience has a question, please unlock yourself. I mean, unmute yourself and ask your question.
I have a question. Kim, can you hear me?
Are you Patricio?
Yes.
Yes, I am asking, are you Patricio?
Yes. Yeah. So my question is, why do you need to consider these partial Legendre transformations to obtain subsystem symmetries?
From this Worldline approach, I mean, the subsystem symmetries is when you go to not to the full system, but a part of it. Therefore, the way that we imagine that we could do that is in doing the Legendre transform and the killing approach to this partial Legendre transformation. That and that is giving the correct results, because we don't care about the whole system at this point for the subsystem symmetries, but only for the for a piece of it. And piece of it in the Worldline approach, it means to, in the Hamiltonian Worldline approach, it means to do a partial Legendre transform. I don't know.
That means you stay Hamiltonian in some variables and Lagrangian in the other ones?
No, the Hamiltonian also is in the same variables where you perform the Legendre transform. Maybe if I am going backwards, if why I cannot go backward? Oh yes. Let me go, for example, in here. The other one that is maybe more clear. Okay, this is the complete Lagrangian in all x, t, and p, and so on. The point is that the coordinates x and y are cyclical. I didn't want to introduce that concept, but when we do that, these px and the x are like parameters, are not dynamical variables of our system. But there is the t, and there is the y, and there is the pi y. That was the Routhian, and I think this is explained in the second volume of Landau and Lipschitz field theory, classical field theory. But I don't know if this answers your question.
Yeah. If, for example, you can do in x, the Routhian, right, and also y, but could you do it?
Yes, in fact, we can
example?
do that, and we have essentially this one that is massless particle in the t y direction, and this other one on t and x direction.
And can you do one for the temporal variable for t, for example? Does it make sense?
No. Okay. I don't know that one is doing the Routhian for the time variable.
Sorry, if I may say something.
Maybe it's my ignorance.
Sorry.
Sorry?
May I say something about this point?
Sure.
I mean, this is exactly what you do in field theory. When you study the subsystem symmetries, you fix one of the momenta, and then you take the Fourier transform with respect to the other one. And this is exactly the same, but translated in, I mean, in this language of the Worldline. The Routhian, to take the Routhian means that you fix one of the variables, and then you are interested in what happens in all the others. As Joaquim showed in the example of the X-cube model. I mean, you take only part of the system and you study what happens there. You study the symmetries of one part of the system.
Thanks.
Thank you, Roberto. Yes, exactly, that's the point. You don't, I mean, this way of proceeding, for example, at least, I think we'll learn from this work of Karch and Ras, where they were doing Fourier transform in one of the variables. And the analogous of that, at this level, it is this Routhian.
Okay, thank you.
I think I may have a related question. So, for example,
since I don't see you, I don't know who is asking me.
It's Frank. It's Frank.
Sorry. Okay. Thank you.
Yes. I mean, I can switch off my camera. I don't know if it will spoil the connection.
Okay.
Okay. Yes. My question is basically, so for example, the XY model, which is the one you explain in more detail. So in the end, I didn't get exactly what are the symmetries you get, because you show first, like, because you should have like some like finite dimensional symmetry group, but then when you analyze this, the subsistence symmetries, then you should get like some infinite dimensional group associated to the subsistence symmetries. So what are you getting exactly associated to each part?
Okay. Let me try to answer this, even with maybe with some limitation. Let's think on the cube, because it's more easy. In a sense, the subsistence symmetry is taking the layers that you could have, the planes, and there you could have a Z2 symmetry for X's and symmetry for Y. Oh, do you hear me?
Yes. Yes, I can hear you.
Therefore, the system, maybe you, yes, if you remove the video, it will be better. Now, what I'm trying to say is that the symmetry on every layer that you have of these two-dimensional layers could depend and do not need to be the same for all the layers. Therefore, you could have in one spin up, another spin down. You could do a lot of things independently for those ones. Instead, for the bigger one, in order to maintain this, if you have a spin up, you should make a spin down. You make for the whole thing. Therefore,
Can I interrupt you 1 second?
Sure.
Yes, because I mean the point is that you are describing the problems is this from this continuous perspective. So actually, I mean it's not easy to see how this continuous or field theory model you introduce is related to the X cube. So then it's for me, it's like at least for me, it's hard to connect what you are doing here with the X cube. However, so my question is,
okay.
No, can you stay? Can you go to the previous slide, the one you had before? No, I mean the
Yes, this one?
No, the one you were showing before.
This one?
No, the next one. So where you compute, I think the Routhian or on the next one, or yeah, I don't know which one. Yeah, this one, the previous.
Which one?
I think it's this. Yes, this one. So for example, here you are saying it's written that. So the subsystem symmetry group is the conformal group in 1 + 1. Is that the statement?
Yes, that is a statement. That in a way, if you wish, yes, that's the statement. Instead, from our perspective, the symmetry of it is given by this final dimensional thing, given by this algebra.
That's what I'm confused about, because the subsistence symmetry is infinite dimensional.
What confused you? The fact that it's infinite dimensional or what?
Yes.
But the fact that it's infinite dimension is not so strange. Let me give an example where this is happening, not for the fracton case, but for example, if you consider a chiral particle, and if you compute exactly in the same way you compute the generator of the canonical point transformations, you find that the solutions, the analogous differential equation, obviously are other ones, admit infinite number of solutions. There are arbitrary functions inside the solutions of your Killing equation. Therefore, for me, it's not strange the appearance of these infinite symmetries at the level of the particles. Because even if you have the ordinary Lagrangian x the massless one, x dot squared divided by e in the relativistic case, and you compute, and you add in two dimensions, and you compute exactly the, if you add in more dimensions, the Killing equation are the conformal Killing equation. In 2 + 1 dimension, the conformal Killing equation becomes infinite dimension. That is the Virasoro algebra, the Virasoro group. Therefore,
Okay.
I don't know what it bothers you.
Okay.
If I have, but I don't know if now is the moment of ask. I have also a question that maybe you could.
Okay. Okay. Let me see if there is another question, and then we can. Yes. Let's see if there is another question, and then we can just like conclude the official part. So, is there another question? Okay, if not, then I thank King again for the talk. So we conclude this official part. I will